Okay, everyone. Thanks for joining the first review call for the Zero Knowledge Proofs grant project with Nervos. We have SecBit Labs here with us today to go through the first milestone checklist. Zhipeng will be presenting from SecBit, and we've got Yu Chong from Nervos side doing the technical review. So without any delay, we'll hand it over to Zhipeng to start the presentation.
Okay, thank you, Ben. Hello, everyone. I'm Zhipeng Sun from SecBit Labs, and I'm glad to be here to share some recent progress of our project. It's a ZKP toolkit, CKB, and we also call. I think I should share screen. Hi, Ben.
Yeah, let me.
You should allow this. Okay. Wait a minute.
Can you share screen now?
I'm looking for the browser.
Oh. Bottom middle. The button bottom middle, the green button.
Yes. I have to quit to enable the sharing. Hi, Ben. I'm back.
Hi. Can you share now?
Let me try it. Okay. Can you see the screen and the pointer?
Yep, can see it.
Yeah, I can.
Okay. Let's try again. Hello, everyone. I'm Zhipeng Sun from SecBit, and I'm glad to be here to share the recent progress of our project. We call this CKB, that's ZKB now, because we think it's easier to remember and call. And yes, let's begin. For anyone who is not familiar with this project, you can just click this URL to see the detailed original proposal and to check the background and the milestones. I'll try to use this diagram to introduce this project briefly. Basically, we divide this into 4 parts. The underlying one is finite field operation and multiple curves. We want to provide as many as crypto curves for developers so they can choose they want. And above this, we want to implement multiple zero knowledge proof systems, including Growth 16, Bulletproofs, Growth 09, Clink, Planck, Virgo. And above this, we also want to provide as many as useful basic circuits or gadgets. So anyone could use these gadgets to build their business logic, basically such as layer 2 or something else. And finally, we want to provide CKB smart contracts, which is ZKP Verifiers on chain. and we want to provide a test environment, unified API scaffolds for circuits and the contracts, and we want to provide many examples and detailed docs for all of this. Okay, and let's recall the primary targets of our project. Firstly, we want to port in ZKP schemes, including growth 16 and the Bulletproofs. We want to implement many other schemes, including growth 09, Planck, and Virgo, and we will implement our own scheme called Clink, which is highly optimized for parallel computation. And we want to generalize the interface of most schemes for developer-friendly APIs. And we want to provide as many as useful gadgets and make them shareable for many schemes. We want to implement on-chain verifier for CKB-VM. Other developers could use them as smart contract libraries for their business. And we want to provide scaffolds for easier development of CKB circuits and the contracts. We mostly want to explore the best practice of ZKP applications on Nervos. Again, let's recall the objectives of Milestone One. We want to provide an early runnable version of toolkit with basic features in the first month. So we choose to add support for the BN256 curves and growth 16 and bulletproof and many basic gadgets, and provide a simple on-chain verifier for CKB. We have released our project, our source code on GitHub and several days ago, and anyone could visit this URL and download to give a try. And we'll push any updates here. Okay, let's check the first part, the underlying libraries of multiple curves. Before started, we investigated several libraries, including Bellman CE. Bellman CE is actually Bellman Community Edition, developed by MetaLabs, and the EXE and the pairing CE and the Bulletproofs implementation from Dalek, etc. Because we choose use Rust language as our main development language, so we almost investigated every famous Rust ZKP libraries on the market, and we finally choose the ZXE because we think his structure fits us, and his active development is important. So we have fork from the EXE, and actually it provides implementation of BLS 12381. It's a curve. It's a pairing friendly curve used by the CAS team, and we ported the BN256 curve from pairing CE to our own library, and actually this curve is used by Ethereum. And thanks to the EXE, we could get a unified interface, and it's quite useful for us to implement many ZKP schemes because we can just switch curves easily. Okay, and we talked about the ZKP schemes just now. We actually added two ZKP schemes in our ZKP toolkit. One is growth 16. It's actually the most widely used ZK snack scheme in the blockchain space for its constant and extremely small proof size and constant and very fast verification. So you know it's quite suitable for smart contracts and blockchain. But one drawback to need trusted setup. We also add Bulletproofs. Actually, we bring in a new implementation of Bulletproofs. And Bulletproofs has shorter proofs and no trust setup required. Okay. One more thing, we designed and implemented Bulletproofs with R1CS. As you may know, Bulletproofs has a different circuit format, which need AL, AR, AO, and several W metrics. It's actually not the same as the standard R1CS circuit format. So we do some trick to do the conversion. And we designed the Bulletproofs with our proof.
I think we just lost you there again, Zhipeng.
Now?
I just caught the end of it.
Right now we can hear you.
Okay. Yeah, and we modified the Bulletproofs protocol to adapt to R1CS. So all ZKP circuits and gadgets could be written once and shareable between growth 16 and Bulletproofs. We have a detailed spec and send to Rinson for review. And I will not go into details of this for now. Okay, and we still need no trusted setup. That means we can keep all original advantages of Bulletproofs. The second part is the third part is gadgets. We have implemented several gadgets, including comparison gadget is non-zero gadget for check if a value is 0 or not, and lookup gadgets and Merkle tree, which could be used for many layer 2 or mixer schemes. and we add a Boolean and MIC hash, which is a ZKP friendly hash. There would be many other useful gadgets to come in the future. Okay, let's talk about smart contracts for CKB-VM. Actually, we want to do off-chain proving and on-chain verifying by using ZKP technology. The smart contracts for ZKP-VM, or we call its on-chain ZKP files, is used for on-chain verifying. Our smart contracts is written in Rust with the help of CKB STD and CKB tool, and contracts can adopt most of the code from the ZKB toolkit core lib, and we can it's easy to test and debug and deploy with the help of Capazzo. And as I know, all these tools is developed by JJY from Nervos, and it's a very cool tools. So the proof of concept smart contract code, we have delivered proofs that we can make a usable ZKP verifier for CKB in Rust without modifying the underlying chain. And we got a baseline on the performance of ZKP verifiers for CKB-VM. Okay, let's check the benchmarks for ZKP files on CKB. We test 2 curves, and we change the optimization level, and we want to compare the binary size and execution cost. And as you can see, BN256 curve could get a much smaller execution cost, which is a term named cycle in CKB. And our test setup is a growth 16 scheme, and with CKB STD, CKB, ZKP, CKB tool with this version, and using the release model and stripped. But how is this performance? Actually, on CKB mainnet Lina, the value of max block bytes is above 500,000, and max block cycles is above 3 billion. So I think the ZKP verifiers for now is we could think it's usable for CKB mainnet. More test results are on this URL, and you can check this. We also provide a command line interface for ZKP toolkit. Actually, we make several gadgets of separate circuits just for a simple demo. So anyone who want to play with this tool, he can just use the CLI to try it easily. And the ZKP CLI support these actions, including a trusted setup, ZKP proof, and ZKP verify. We also got multiple scheme options and curve options, and we can choose the input and output format. such as we can use JSON format. We got examples. Let me try to explain this command and the output one by one. Firstly, we run the trust setup for the MIMC circuit, and we got the proving key and the verifying key the file, and later we'll use it later. The second step is to run ZKP proof using the MIMC circuit, and we can pass in the string, which is a secret string directly, and the proof files are generated in JSON format, and we can store the proof files. These are some curve and gadget names, and the important ones are the params and the proofs field. Actually, the param field is the public input of the circuit, and the proof are the proof result of group 16. Okay, let's run the ZKP verify command with this proof file as the input, and we can see it start to verify, and the verify result is true. It means that someone knows a secret screen whose MIMC hash is this value. Okay, if we edit the proof file, in this example, I actually changed a random bit in the proof field, and I run the ZKP verify again. The verify result is false in the last. So it's called soundness in ZKP. You can check this URL for instructions of ZKP verifier contract test. It will need more testing steps and will cost much longer time. I will not do the demo here. It actually most time is waiting for its execution. Okay, and in the last, I want to talk about the next steps for milestone 2. And firstly, we will implement more ZKP schemes, including Clink. Clink is a new scheme designed by us. It's optimized for parallel data processing, and we will implement growth 09. It's a lightweight ZKP for linear algebras and matrix operations, and we will implement Virgo. It have almost linear proving time and big O log n proof size. Still no trust setup required, and we will provide more ZKP verifiers for ZKP-VM. And actually, we are still turning the Bulletproofs implementation, and it's actually runnable for CKB-VM. It's a working in progress work. And we will work with Nervos core team to improve performance and usability of ZKP verifiers. We will implement more useful gadgets, and so later you can use ZKP toolkit CKB to design the complicated business logic. And after that, we will provide better examples of how to use this toolkit and how to and how to use the smart contract. That's all. Thank you. Thank you for listening. Hi, Ben.
Hey, thanks so much. Great to see the presentation. So we'll hand it over to Yuchong now. If he has any specific questions or clarifications or feedback on the presentation.
Thank you for the presentation. Can you hear me?
Yes, I can hear you, Yuntong.
Okay, I think this work is really impressive, and Milestone One target has mostly been achieved. Most of the questions I think I've already asked in the Discord before. I've got a new question. I'm a little bit confused of the gadgets in the enumeration gadgets type defined in the lib.rs file in the source directory. I see that you defined 4 gadgets: a mimc, a greater than, a less than, and a between. And
yeah.
And then and I also saw that you in the CLI directory you only implement the mimc and range proof. So what's the relationship between this mimc and the range proof and this the 4 gadgets you defined in the lib.rs file? Which is the underlying gadgets and which are the functionalities that you can use in a high level?
Okay. Actually, we implemented the range proof, or call it a comparison gadget, for the underlying, and we make them. You compare values. You could compare it by greater than or less than or between. So we just use these 3 gadgets to help users to use the comparison gadget more easily. And actually, it's just for CLI usage, and it's the same thing as the comparison gadget. We think we would refactor the CLI or set examples in the future when more gadgets and schemes added. That's all.
Okay. And what about the gadgets that you listed in the gadgets directory, the Boolean, the lookup, one bits, and Merkle tree? How can we use them to prove some real life functionalities now? For example, the Merkle tree or the Boolean or something, or all these gadgets, how can we use them to prove some?
The Boolean and the lookup circuit is actually very low level, and we could implement other gadgets using this Boolean and lookup gadget. And the Merkle tree gadget, I think it's still not usable for normal developers, because we still not adding hashing the the other hashing algorithm gadget here. I think we could use the merge tree gadget in next milestone, and we would change the gadget's format for easier combination, as you mentioned on Discord. It actually all circuits, all gadgets is more used for demo and not for real business for now.
Okay. And I just noticed a small detail that I noticed that most of the curves are the code you are just ported from ZKP, but not BN256. Did you implement it yourself?
Actually, we ported it from parent CE. It's a library developed by MetaLabs, and it's also ported or forked from a parent library developed by the ZKP team, and we ported the underlying code with the modifying interface to make it fit in our library, or to say the EXE interface. And I noticed that the EXE itself also got a new PR for BN256. We could compare the different implementations and to decide we would keep the current implementation or just merge from the EXE library. Yeah.
Okay, I think that's all I have to ask. Thank you.
Okay, thank you, Yunzong.
Great. Okay, thanks, guys. Is there any questions from anyone else on the call? If you have a question, feel free to unmute, or you can also post it in the chat. We'll give that a couple of minutes. Otherwise, if there are no other questions, just want to thank both of you guys for joining the call. Zhipeng for doing this great presentation. I think the Zero Knowledge Proof grant is definitely one of the most exciting grant projects that is ongoing. So I think everyone is very excited to see this great progress, and also looking forward to the next review call. Okay, it looks like we don't have any questions, so we'll finish there. Thanks again to everyone for joining the call, and see you next time.
Okay, thank you, Ben. Thank you all.
Yes, thanks.
Thanks, everyone. Cheers.
Bye.
Bye.
Bye.